Well, I am really happy today. So this is the first time that I've used electronic homework in one of the classes. And I was so happy when I looked this morning at 9 o'clock and found virtually everybody had engaged with the homework assignments. And so much of learning organic chemistry is actively working problems and actively trying to understand things that I was really, really excited to see people are coming along with me on this process of learning, and it makes me very, very happy. So today we're going to continue our discussion of chapter 20, and I'd like to introduce organometallic reagents and talk about their reactions with carbonyl compounds and their reactions in general. And then we're going to talk about reactions of members of the carboxylic acid family with hydride nucleophiles and with organometallic reagents. And if there's time, we'll conclude by talking about use of these reagents and these reactions in synthesis. So when we were talking last time, we talked about hydride reagents with ketones and aldehydes, and we said sort of generically, if we have some ketone or aldehyde, now I'll write it generically, just showing R groups that could be alkyl, that could be aromatic, that could be hydrogen. So generically, a ketone or aldehyde. And we envision its reaction with some hydride nucleophile. Now remember, when I'm writing something like this, H minus in quotes, of course, there's no reagent that is itself a hydride nucleophile, but these are things like lithium aluminum hydride and sodium borohydride that serve as sources of hydride. And then if we carry out a workup with aqueous acid, H3O+, or in some cases you can use water. And again, I'll put this in quotes because you can't go and buy a bottle of H3O+. You could take sulfuric acid and pour it into water to make hydronium ion and bisulfate ion. You could take HCl in water and make H3O+ and chloride ion. And so you'd go to the stockroom and ask for one of those. When you do that, you get a reduction of the ketone or aldehyde and protonation like so to give an alcohol. Now, what I'd like to do at this point is to consider an analogous reaction, again, written at this point as an abstraction. So again, we'll take our ketone or our aldehyde, and we'll imagine instead of adding our hypothetical hydride anion, we're going to add something that I'll say is R minus with a lone pair of electrons, meaning a carbon-based anion. We'll talk more about it. Not necessarily something you can get as a free anion, and certainly not something that you could put in a bottle on its own. It would be part of an organometallic reagent. But again, right now we're getting our view from 30,000 feet. And again, if you imagine some type of aqueous workup with H3O+, now, instead of adding in hydride to our carbonyl compound, we've added in an R group. The use of primes and double primes and so forth is just my way of representing that there are various groups different or the same. Anyway, but again, in the view from 30,000 feet, the profound thing about this reaction as I've written it is that we formed a carbon-carbon bond. And so much of organic chemistry, both the practical aspects of synthesizing useful molecules and the real intellectual beauty of the discipline, is the fact that we can create great degrees of complexity, valuable complexity, medicines, analogs of natural products that are too scarce to get otherwise, probes to probe reactions and probe biology. We can do all of this through chemical synthesis, in which we take little molecules that might be able to be purchased and build them up into big and complex and useful molecules that can cure cancer or fight disease or teach us things. So now we come down to the issue of what is our R-, what is our source of our carbon nucleophile? And the first really, really valuable carbon nucleophiles that were developed were Grignard reagents, developed by Victor Grignard. He received the Nobel Prize in 1912 in chemistry for this. And the basic idea is that you take some halide, a bromide, a chloride, or an iodide. Fluoride is sort of the oddball among halogens, and if you go down your periodic table to astatine, it's not stable, it's radioactive, so organic chemists would never work with it. You can't really isolate it. Anyway, if we take an alkyl halide such as butyl bromide, and we treat it with magnesium metal, if you've done one of these reactions in the laboratory, you'll have seen your magnesium metal is kind of bright and shiny and lightweight. It comes as turnings that have been worked off a big block of magnesium with a lathe. And you'll put them with your alkyl halide in a solvent. The solvent will be an ether solvent, either ether or THF typically, although sometimes other ethers can be used. THF is tetrahydrofuran. It's a cyclic ether, so it's an ether with a 5-membered ring, and it has lone pairs. It's kind of like diethyl ether with its ears pinned back. And either of these work well. The result is that you get a Grignard reagent. I started with butyl bromide here, and so I'll write the Grignard reagent from butyl bromide. We call this butyl magnesium bromide. And the ether solvent coordinates to the magnesium. The magnesium doesn't have a complete octet here. We have only 4 electrons around it, 2 from the alkyl group and 2 from the bromide. And so the ether solvent, the diethyl ether or tetrahydrofuran, will coordinate to the magnesium and help give it the feeling of having a complete octet. Anyway, as I said, the broader category of this is a Grignard reagent. And you can make these from anything from bromo or chlorobenzene to alkyl bromides to methyl iodide. And so this typically one makes a Grignard reagent as part of a synthetic process. They're actually stable reagents. You can put them in a bottle. You can buy them. But in the laboratory, because they react with air and because they react with moisture, you would typically go ahead and immediately add a carbonyl compound. So let me show you a typical synthetic carbon-carbon bond forming sequence that one might do in the laboratory. So we might take our butyl bromide and treat it first with magnesium and ether. You'll often see people write a slash in an equation. Often that slash is a way of saying the solvent is below the slash. Or if we're just writing a simple line of equation, we might put our solvent below the arrow. Then let's add a carbonyl compound. And for the purposes of teaching, for the purposes of this example, I'll take acetone as our carbonyl compound. And finally, let's do an aqueous workup. And I'll choose an acid here. Let's say aqueous HCl as the acid I would choose. And the product of this reaction now is a carbon-carbon bond forming adduct, or an adduct with a new carbon-carbon bond. If you wanted to name the compound, we've now formed a 6-carbon chain. So it's 2-methyl, 2-hexanol as our product. So this is very powerful because now we've taken some small compounds that you can buy and we've made a more complex molecule that you might not be able to buy. Many molecules with this type of structure, these types of structures like alcohols with long chains on them, are insect pheromones, for example. So some of these types of synthetic products are used to make traps for insects like Japanese beetles, where the pheromone will lure the insect to the trap and then they'll fall in and die. All right, so I want to talk a little bit about the properties of Grignard reagents and organometallic reagents in general. So metals, of course, are much more electropositive than carbon. So any bond between a metal and carbon is either going to be a polar covalent bond or an ionic bond. If you want an index value, or chemists like to keep electronegativity values in their head, it's a useful way of assessing the degree of polarity of a bond. Magnesium has an electronegativity of 1.3, carbon about 2.5 or 2.55. So you can think of the bond between magnesium and carbon as a polar covalent bond. In other words, you can think of this as having a delta minus, a partial negative charge on carbon, and a partial positive charge on magnesium. Sometimes if you're writing a mechanism and you want to be quick about it, you could say, well, I'll write a non-bonded resonance structure. Even though I know it's primarily a covalent bond, I could write an ionic bond resonance structure. So we could think of it as this. Maybe I'll put this in quotes here just to remind us this is sort of our thinking. And so if I'm thinking about this from a mechanistic point of view, one way we could think about this, I'll take our acetone and our Grignard reagent written generically. One way we could think about this is that our organometallic reagent serves as a nucleophile. And of course, we draw a curved arrow mechanism. We help think about the flow of electrons and bonds by starting an arrow at the lone pair at the available electrons, either as a lone pair or in a bond, and then moving to the thing that wants electrophiles, in other words, from the nucleophile to the electrophile. As we did in thinking about hydride mechanisms, we can't go ahead and now have 5 pairs of electrons around this carbon atom. So concurrently, as the nucleophile moves in, electrons move up onto oxygen. And so we continue our grammar, if you will, of writing our curved arrow mechanism now, writing a product in which we have our negative charge. And if I want to be good, organic chemists are rarely good. We love to throw away things that aren't necessary in our thinking, but if I want to be good, I'll draw the magnesium counterion there. We can also think of this just as we did with lithium aluminum hydride, maybe a little more correctly, or certainly a little more sophisticatedly. We can think of our covalent bond and keep in the back of our mind that it's a polar covalent bond, and write a curved arrow mechanism in which we simply go ahead and now take the electrons from that bond, move it in like so, and again, come out to the self-same product. So these are good ways of thinking, sound ways of thinking about the mechanism of the reaction. So one thing to keep in mind about Grignard reagents, and indeed about most organometallic reagents, particularly ones in which there's a large difference in electronegativity between the carbon and the metal, is that organometallic reagents, like Grignard reagents, in general act as very strong bases. We can think about basicity in terms of the pKa of the conjugate anion. So if you have butyl magnesium bromide, the conjugate anion corresponds to an alkane. In other words, where in the conjugate acid you have a CsP3 carbon bound to a hydrogen, the pKa for such a hydrogen is about 50. That's about at the very end of the basicity scale. That's about as basic as you can get for a carbanion. If you have an alkene, now you have a CsP2 carbon bound to a hydrogen. The electrons are held a little more tightly in this type of structure. The pKa now is about 44. A way of thinking of this is, since the electrons are a little more stabilized, held a little more tightly in an orbital that has more S character, right? sp2 has 33% S character, sp3 has 25% S character. As you hold electrons more tightly, the CH bond is more willing to give up H plus and give you a carbanion. So an alkene is a little bit more acidic than an alkane. These are all compounds I call very weak acids, and I usually put quotes around the acid because you would not get any evidence of acidity from the compound, say dissolving it in water and testing it with a pH meter. And yet in a Lewis acid, Lewis base reaction, you can think of an alkene, say, as a proton donor under certain circumstances. Now, by the time you get to an alkyne, now you've got 50% S character in your CH bond. And now these are reasonably acidic. They're still very weak acids. Your pKa is only 25. That's really, really, really weak still. It's not even like water, which you think about as an acid forming hydroxide anion. It's still a very weak acid, or alcohol forming an acid, giving up a proton and forming an alkoxide anion. And yet our pKa is about 25. And I'll show you an implication of that in just a moment when we start to talk a little more about alkanes. But the point of this comes back to what I was saying before about about Grignard reagents being very reactive toward water. A Grignard reagent acts as a base with water, and so if you expose a Grignard reagent like butyl magnesium bromide to water, the water acts like a Bronsted acid, and you get butane and bromomagnesium hydroxide, a mixed salt here. So this is a Bronsted acid, Bronsted base reaction, if you think about it. We have water acting as an acid on the left half side of the equation. We have our alkane as an acid on the right side of the equation. And because the pKa difference is so humongous, the pK of water is 15.7, the pKa of butane is about 50, I don't even bother to write an equilibrium arrow. The equilibrium constant is 10 to the 34th, right? It's 10 to the difference in pKa's. That reaction lies so far to the right that there's just no component to the left on it. And that's true with whether it's with water or an alcohol. And so just by comparison, imagine for a moment I wrote, let me pick a particular alcohol. We'll pick ethanol as an alcohol. And so now we would get butane and a ethoxy magnesium bromide. And of course, this would be the same with a carboxylic acid or just about anything that you would normally think about as even mildly acidic. All right, well, Grignard reagents are one of a broader family of organometallic reagents. Another member of the family that reacts very, very similarly are organolithium reagents. And so if we wrote Grignard reagents sort of generically as RMGX, that would be a generic way of writing a Grignard reagent. We can write organolithium reagents generically as RLI. Organolithium reagents are formed by reacting alkyl or aryl halides. Again, we're talking iodide, bromide, chloride with lithium metal. If I write a balanced equation, say, for bromobenzene and lithium, it takes 2 lithiums. And that makes sense if you think about it, right? We're carrying out a 2-electron process here, and lithium has 1 electron. So magnesium has 2 electrons. And so a balanced equation becomes that we get phenyllithium plus lithium bromide. And again, organic chemists are awfully, awfully bad about writing products of reactions. So I'll put the lithium bromide in parentheses because I might not write it. So typically, if I were writing this as, say, a synthetic reaction, and I imagine generating an organolithium compound and, say, reacting it with an organic compound, I'll give you an example of what I might write. So I might take bromobenzene, or I might take chlorobenzene if I wanted, treat it with lithium metal. Now, organolithium reagents can be generated in ethers, and ether can serve to coordinate, but they also form clusters, and so they actually can be generated in other solvents, including hydrocarbons. I'm just going to skip the solvent here because it's much less important than in a Grignard reaction. And let's say as my partner, since I gave you a ketone before, I'll take an aldehyde. The aldehyde I've chosen is pivaldehyde. That's the trivial name. Or 2,2-dimethylpropanal would be the IUPAC name. And again, I'll imagine doing some type of aqueous workup. I'll just write H3O plus here to indicate I haven't specified the acid. It could be aqueous HCl. It could be aqueous sulfuric acid. One that I personally like to use in my own laboratory is aqueous ammonium chloride, which is a very mild acid and very good for workups of reactions like this. Anyway, after our workup, the product now has a new carbon-carbon bond, like so. And of course, because we've generated a stereocenter in the molecule, we've generated it as a mixture of two enantiomers. We've generated two different enantiomers in equal amounts. We've generated the racemate. All right, in part because your textbook mentions various different organometallic reagents at this point, I want to follow along, and in part because I want to remind you of what I think are really useful items, and in part because I want to tie into this concept of pKa. I'd like to, at this point, talk about acetylide ions. And I see I have a question.
Yeah, you sort of erase the equation, but for the second equation, what magnesium bromide is attacking the ethanol, why doesn't the magnesium bromide bond to the OH, but instead bond to the ethanol?
What's that? Oh, the question was, why doesn't the magnesium bond to the OH? It doesn't, well, there's no OH. Oh, you're saying in that reaction, because the ethanol has now given up its proton to react with the butyl part. So the proton has come off of the ethanol onto the carbon of the butane, leaving an ethoxide anion which combines with the MgBr plus component.
Wouldn't the same thing happen with water?
And it did. So we had, in the case of ethanol, we had ETO-MgBr. In the case of water, we had HO-MgBr. So we had a very analogous reaction. Another question.
In that second equation, are we supposed to have two lithium?
Ah, great question. In that second equation, are we supposed to have two lithiums? This is very typical of how organic chemists will write a reaction. So typically you would see that one might not, particularly as you became more used to writing reactions, it might be implicit, but indeed you would have two lithiums. So you could easily envision writing lithium parenthesis 2 equivalents or 2 lithium. And again, this is very much part of the shorthand of writing organic reactions, particularly when focused on synthesis. Good questions.
So will organolithium reagents not be created if we don't have two lithium?
Ah, great question. Would organolithium reagents not be created if you had only one lithium? Well, now imagine what would happen would be you'd have 1 mole of butyl lithium, 1 mole of butyl bromide, 1 mole of lithium. You'd get half a mole of butyl lithium. Now, here's where the fun comes in. If I let that sit at a low temperature and used it quickly, I would have a reaction of 1 mole of butyl lithium, of 1/2 mole of butyl lithium. But if I let it sit or tried to put it in a bottle, and I now had that organolithium reagent sitting for a long time with more butyl bromide, I would get E2 elimination, or because the reagent is strongly basic, to give butene and butane, or I would end up having SN2 displacement to give octane, or both. Great question. So yes, I would definitely use 2 equivalents. All right, well, at this point, I want to talk about acetylide anions and sort of follow along with our textbook, but also because thematically it fits in. So as I said, acetylene, alkynes in general are especially acidic. While they're still very, very weak acids, pKa of about 25, they're strong enough acids that very, very strong bases can pull off their proton. So for example, if I treat an alkyne with sodamide, I get the sodium acetylide anion Now, sodium's a little more electropositive than lithium. Lithium has an electronegativity of 1, sodium of 0.9. By the point you get to organosodium reagents, they're pretty ionic in the bond. So I generally think of these as ionic.
Sorry, is it NH2 or NH?
Great. NH2. NaNH2 is sodamide. And if I'm going to balance my equation, and as I said, organic chemists are usually very bad about this, ammonia, thank you. Thanks very much. Ammonia is the other byproduct of reaction. And now we see ourselves very much in the situation of a Bronsted acid, Bronsted base reaction. So we have pKa of about 25 and pKa of about 38. And so a difference of pKa means that equation lies way, way, way to the right, 10 to the 13th equilibrium constant or thereabouts. So basically, I throw 1 mole of sodium amide, 1 mole of an alkyne, and I get essentially all acetylide anion. And I'll write a balanced equation, or I'll write a synthetic equation here in which I say take propyne, I treat it with sodamide, NaNH2, which you can make by dissolving sodium metal in ammonia with a little bit of iron, and it reacts to give sodium amide. And for the heck of it, again, I'm just trying to give us a range of carbonyl compounds. For the heck of it, I'll take 2-butanone. And then since I mentioned that I like aqueous ammonium chloride as a source of acid for a workup, I'll just demonstrate what I would do in my own laboratory, which is to use aqueous ammonium chloride. And the product of this reaction is this. It is the alkyne with the alcohol. This is, of course, racemic. In other words, your textbook points out very nicely that you're going to add your nucleophile from both the front face and the back face of the carbonyl. And so we have one enantiomer in which the OH is pointing back and the alkyne is pointing out. We have another enantiomer in which it's added from the back face, and now the OH is pointing out and the alkyne is pointing back. And we will get equal amounts of these, both of the R and of the S. Although this chapter is focusing primarily on carbonyl compounds, it's also beginning to introduce ideas of organic synthesis and carbon-carbon bond-forming reactions. And so your chapter reminds you that you've already seen certain carbon electrophiles. So for example, you've already seen epoxides. So there are lots and lots of types of electrophiles you can generate your compounds with, that you can react your acetylides and other carbon nucleophiles with. And I'll just point out one example here that brings out a couple of additional points. So butyl lithium is commercially available. It's a common source of a highly basic organometallic reagent that can be used not only as a nucleophile, but also as a very strong base. And so butyl lithium is a great reagent for pulling off moderately acidic protons, for example, protons from alkynes and also protons from amines like diisopropylamine, which you'll see later. Anyway, butyl lithium would react with our alkyne. Remember, our pK of the alkyne is about 25. Our pKa of butane is about 50. And so it would react again in an acid-base reaction to give now an alkynyl lithium reagent. And so we can use this as well as a way of making anions. And I'll just give you one example, or this as well as a way of making carbon-carbon bonds. So just to give you some diversity in your chemicals, in the molecules that you see, I'll take, say, phenylacetylene, and we could envision treating it with butyl lithium. You'll often see butyl lithium written as N-butyl. N means normal. Normal is just a fancy way of saying it's the regular, it's the one butyl lithium, rather than, say, the lithium being at the 2 position of butane, which is called sec-butyl lithium, or being on a tertiary butyl group, which is called tert-butyl lithium and is a stronger base. Anyway, let's envision using the common reagent N-butyl lithium, treating our phenylacetylene with it. That's going to give us our lithiated phenylacetylene, our organolithium compound. And just to demonstrate the point of other reactivity, we can picture the reaction, say, with an epoxide, and then again an aqueous workup, H3O plus. And the product of this reaction is an alcohol, just as we've been generating in all of the reactions I've shown thus far. But what's interesting about this is now the alcohol, instead of being connected directly to the carbon that had been, or directly to the carbon where the nucleophile attacked, it's 1 over. You can think of this as R and the alkyne lithium reacting with the epoxide, and so we're going to draw electrons flowing from the carbon-lithium bond into the carbon-oxygen bond, pushing electrons onto oxygen and opening up our ring. All right, so what we've done at this point is we've really overviewed a fundamental reaction of carbonyl groups, and we've introduced these reagents that make for very, very strong nucleophiles, hydride nucleophiles like lithium aluminum hydride in particular, to a lesser extent less reactive sodium borohydride, and then various organometallic reagents like Grignard reagents and organolithium reagents. At this point, I want to sort of broaden out our thinking and start to talk not just about ketones and aldehydes, but more broadly about the reactivity of the carboxylic acid family. And to just put this into context, I mean carboxylic acids essentially all compounds in which we have carbon in the +3 oxidation state. I will get to the several questions in just a moment. Esters being another member of this family. Acid chlorides. So I'm going to paint with a very broad brush, and later on we're going to get to a more specific understanding of the reactivity of this broad family. But right now I'm going to paint with a very broad brush. I'll include in the family acid anhydrides. And maybe to wrap up in main members of the family, I'll talk about amides. But before we discuss their reactions with organometallic reagents, I saw several questions. I think there was one here, one there. Yes? Ah, great question. The question was, when the lithium attacks the epoxide, does it attack from the top or the bottom? Does it occur with inversion of stereochemistry? And indeed it does, although there is no stereochemistry at the center that we formed here. You could imagine, let's say, having two different substituents here, like a hydrogen and a deuterium, and we would get inversion of stereochemistry. Typically, epoxides are attacked by nucleophiles, by basic nucleophiles, at the less sterically hindered carbon. So for example, if I had the epoxide with a methyl group called propylene oxide, this one is trivially called ethylene oxide. If I had the epoxide with a methyl group on one side, propylithium, the alkyne would attack the carbon that didn't have the methyl group on it. Does that make sense to you? Another question, I saw one young lady. Same question, and?
Why do we like to use butyl stuff so much?
Why do we like to use butyl stuff? Great question. So all of our hydrocarbons ultimately come from petroleum. And so one of the ways in which butyl lithium is made is by first cracking, heating petroleum very hot to get smaller fragments. And one of the fragments that's easily isolated is butene. And the butene can then be taken on to various types of products, including butyl bromide, for example. So this is one of the reasons that butyl is used. You can buy propylithium, but you can buy great big bottles of butyl lithium. Methyl is another common one.
So the chemistry industry relies on fossil fuel?
Does the chemistry rely? Oh, I love that question. Yeah, almost all of organic chemistry ultimately goes back to petroleum. Some of the chemicals that we use as simpler building blocks come from other sources like carbohydrates and modern, not ancient plant sources. But yeah, almost all of organic chemistry comes back to petroleum. So the seats that you're sitting in have a plastic that may be it's polypropylene or something, and a covering that's a synthetic fabric like nylon. All of those have come from petroleum. And so I look at petroleum, as much as I hate to pay $4.30 at the pump, when I think about the amount of stuff you're getting a gallon of gasoline. This is too valuable to be burning up because there are so many things that you can make from it. You can't get a gallon of anything. You can't get 8 pounds or 7 pounds of anything for $4. I can't get a gallon of beer for $4. And yet we go ahead and we burn it. So yes, petroleum is incredibly valuable to organic chemists. And one of my dear colleagues' favorite questions, one that I won't be asking you on an exam because it's too open-ended and far too ridiculously complex for you at this point in your sophistication, is to go ahead and write a synthesis of a steroid, let's say cholesterol or testosterone. You've seen in your current chapter some steroids, starting with petroleum. So that would be one of her favorite questions. All right, but I want to go now to the reactions of esters and of various members of the carboxylic acid family. And I thought your textbook's presentation, particularly in the reduction section, may have been a little bit confusing because there are a lot of subtleties. And when I think about a subject, I like to think about it in terms of sort of the general rule and then exceptions to it. And there are a ton of little exceptions, and your textbook has picked one, and they're talking about lithium aluminum hydride with amines or with amides, and we'll talk about that later. But right now I want to paint with a very broad brush a sort of general reaction of lithium aluminum hydride. There are these strong nucleophiles, these potent nucleophiles. Hydride sources, particularly lithium aluminum hydride, just reduces the crap out of everything. Alkylithium reagents like methyl lithium just add to everything as much as they can. Ditto for Grignard reagents with certain exceptions. So again, a very broad brush view from 30,000 feet, but we're going to take a specific reaction. We're going to take methyl benzoate here to exemplify our point. We're going to imagine treating it with lithium aluminum hydride. I'm deliberately writing this as a synthetic reaction. We'll talk about what's happening in a moment. And then an aqueous workup with, I'll just write generically H3O+. And you might do this reaction, say, in THF. And I'll be a good person and write a balanced equation, or at least, actually, I won't write a balanced equation, but I will at least write my two organic products of the reaction. Your organic chemist is typically focused on the big stuff, but I'm going to write this product, benzyl alcohol, and the other organic product, methyl alcohol, methanol. And collectively, then, these two constitute the organic products of reaction. And what this ends up illustrating is a new property that we haven't yet seen called an addition-elimination reaction. And we're going to see that this addition-elimination reaction goes through an intermediate of benzaldehyde. And to a certain extent, maybe with the exception of amides here, if I took any of the compounds that I'm erasing and treated them with lithium aluminum hydride, you would get a similar reaction of them. All right, so as I said, this is a big mouthful, and I like to bake big mouthfuls into bite-sized pieces. So let's think in sort of broad mechanistic terms here. All right, I'm going to think about, I'll write out our benzoate component. I'll write out our methyl benzoate. And I will, at least for the moment, try to be a good person and write a good mechanism in which I write lone pairs of electrons and try to keep track of my charges. And to keep things simple, I'm going to write, rather than writing out all of lithium aluminum hydride, I'm going to write hydride just as this abstraction of a hydride anion. And the first thing that hydride does is it's a good nucleophile, a potent nucleophile. We've talked about the reactivity in general of carbonyl groups. The carbonyl group is an electrophile. Electrons flow from the nucleophile to the electrophile and on to the oxygen. And I'll try to be a good person and write all of my lone pairs, all 3 lone pairs of electrons around the oxygen, and then 2 on this other oxygen. Now, this is not a stable species. This is not something that you can isolate. It's an intermediate. And so I'm going to remind us of the fact that it's an intermediate by drawing it in a bracket. We have a special name for this intermediate because we've gone from a trigonal carbon, a carbon with 3 things around it, to a tetrahedral carbon, a carbon with 4 things around it. I'm going to call it a tetrahedral intermediate. And as I said, the tetrahedral intermediate isn't stable. The tetrahedral intermediate can break down. Electrons flow back down from the oxygen. They push out methoxide. And now we get a new carbonyl. At this point, we've gotten benzaldehyde, the intermediate that I mentioned, and methoxide anion with its 3 lone pairs of electrons on it. The reaction doesn't stop at this point. Esters are less electrophilic than aldehydes. In other words, aldehydes are more electrophilic than esters. We can write resonance structures for esters, or a resonance structure in which the methoxy group donates electrons into the carbonyl and makes it less electrophilic. Aldehydes, on the other hand, have less going for them. And so we have more nucleophile, and you can't just stop at this point. It's going to further get reduced. And so here's our aldehyde. Here's our H minus again. And again, I'll try to be a good person and put it in quotes. And electrons flow from our hydride onto the oxygen, now to give rise to an alkoxide anion. And at this point, that's what will sit around in your flask. I haven't drawn the counter ions or anything until you do a workup. And I'll just write this as workup, meaning adding some acid or adding some water. I'll put this again in our sort of 30,000-foot view of H+. And the product of this reaction is benzyl alcohol. And the other product of the reaction is we'll also protonate our methoxide. So the other product of our reaction is methanol. And I'll just put that in parenthesis here. All right. So I want to show you some generalities. I want to show you some analogy in this. And so at this point, I'll write essentially the same reaction with just a slight difference on it. So before, we could have been thinking about lithium aluminum hydride. I said let's consider lithium aluminum hydride. At this point, let's consider methyl lithium. And so I'll take our same ester, I'll take methyl benzoate, but I'll treat it first with methyl lithium. And I'll write in parentheses 2 equivalents. I'll try to remind us that we're using a full amount of it. And then secondly, we'll treat this with some aqueous acid. And the product of this reaction now, instead of adding in 2 hydrides, instead of adding in 2 hydrogens, we've added in two methyls. It's essentially the exact same thing. And so now we've gotten an alcohol as our product in which we've added in two methyl groups. The reaction's going to go just like on the other one. We went via benzaldehyde. Here, the reaction's going to go by way of the ketone called acetophenone. But just as in the case of the other one, we can't stop at the ketone with one equivalent of methyl lithium. The ketone is more reactive than the ester, and so as it now is sitting around, it immediately reacts as well. And so that's our sort of view at 30,000 feet of the reaction of these very, very strong nucleophiles with members of the carboxylic acid family. As I said, there are some exceptions, some differences, but we can kind of catch this general spirit of this on the following equation. And so I'm going to write this. I don't always like the way your textbook presents things, particularly with a lot of abstractions, because from my way of thinking, it's easier to start at the concrete and then work to the abstraction. For a computer, I think it's very good to like start with an abstraction and it can spit out all the examples. But we've just looked at two examples. So now I'm going to write the abstraction, and I'll say many members of the carboxylic acid family. And I'm going to write, again, this sort of abstraction of Nu minus ... So some type of strongly basic nucleophile that encompasses all of the reagents that we've been talking about. So I'll say strongly basic nucleophile that includes, for example, lithium aluminum hydride, RLI, organolithium reagents, RMGX. In other words, all of these species have in common that they have a bond between a metal, relatively electropositive metal, and a highly electronegative species, hydride, or I'm sorry, a more electronegative species, hydride or lithium, or carbon. So basically, the generalities of this type of reaction are that in general, we get, and I'll write parenthesis excess here just to avoid confusion. When you have excess, in general, you're going to observe addition of two equivalents of your nucleophile, which I guess I've written as Nu. Plus Z minus. So that would sort of be the biggest abstraction. And I guess I'll try to be good and keep my electrons in check. So I'll write a balanced lone pair. All right. So what we've looked at here what we've looked at here is an addition-elimination reaction. And we've seen this general principle that when you have something like a methoxy group on a member of the carboxylic acid family, the reaction doesn't stop. Things go on. Now, to many students, the first time they see an addition-elimination reaction, they find it confusing. And here's why they find it confusing. Here's our, let's say, our ester. And we've just added a nucleophile to it, Nu-, to form our tetrahedral intermediate. And that tetrahedral intermediate isn't stable. It breaks down. It kicks out the OR group. In other words, our electrons flow like so to push out our OR group that serves as a leaving group. And the first time people see this, having already been through 51B and learned an SN2 displacement, was it 51B or 51A you learned SN2 displacement? A. 51A and seen an SN2 displacement reaction, people start to think about this and say, whoa, what's going on here? We don't see an OR group like a methoxy group leave in an SN2 displacement reaction. But this is a little bit different. Here, a less basic leaving group is okay. See, in an SN2 displacement reaction, you've got to crowd 5 things around carbon. You don't have a stable intermediate. That leaving group was perfectly happy attached to the carbon, and yet something's coming in and pushing it out. And it's going over this high energy barrier, this transition state, to make that atom leave. And so that atom that leaves has to really, really want the electrons. In other words, a good leaving group in an SN2 displacement reaction has to go ahead and have a very stabilized anion, or conversely, because stability of the anion means acidity of the conjugate base, conversely, a strongly acidic conjugate base. So in this case, it's a little different because there's nothing bad about the tetrahedral intermediate. We haven't had to crowd anyone in here. It's easy to get to this point. But now it can happily kick out the OR group, and what it gets in return is a carbon-oxygen pi bond, which is very strong. And so there's no problem in getting your tetrahedral intermediate together. It's not pentavalent. There's nothing bad about it. But it's very good to go downhill and to break down and kick out the leaving group and get back your pi bond. So what I always like to think about here is in an SN2 displacement reaction, you've got to have a good leaving group. But in the case of this reaction, an addition-elimination reaction, a less basic leaving group is okay. And by comparison, I'd say maybe less than 5 pKa is good for a leaving group in an SN2 displacement. Or maybe even an E2 elimination. Thoughts or questions at this point? Doesn't it work like a substitution? Indeed, this is a substitution reaction. So the very first step of our methyl lithium plus methyl benzoate reaction was to substitute the methoxy group for a methyl group and get acetophenone. And then, of course, we couldn't stop at acetophenone because it's even more reactive than methyl benzoate, so another equivalent of methyl lithium adds. But indeed, it is a substitution reaction. Unlike an SN2 substitution reaction, here you can have a leaving group that's a little bit less acidic, like an alcohol or an alkoxide. If you added a water and acid, guess I'm not exactly following. You mean, oh, you mean in the second step, would we, yes, if we, so in the workup with acid, we would protonate, indeed. And one more question.
What does it mean by leaving group has less than 5 pKa?
Okay, what do you mean? Great question. What do you mean by a leaving group has less than 5 pKa? In an SN2 displacement reaction, chloride, bromide, iodide are wonderful leaving groups. pKa of the conjugate acid, respectively, about -6, whatever number you use, about -6 for HCl for the conjugate acid, about -8 or thereabouts for HBr, about -10 for HI. And you can go a little bit less good leaving group. I can write an equation, I can give you an example of a case where instead of having a very strong acid counter, for the conjugate acid in an SN2 displacement, you could go slightly from -6 for chloride, into the positive range. I could give you an example as low as 5 for the pKa. Beyond that, in an SN2 displacement, it pretty much isn't going to occur unless, like in the case of an epoxide, you have ring strain. pKa of the conjugate acid in an epoxide is 17 for an alcohol, but you've got that roughly 30 kilocalories per mole ring strain associated with the oxirane ring, making it pop open. So that's the rare case in an SN2 displacement-like reaction where you can actually have what's essentially alkoxide as leaving group, but it's spring-loaded. However, in the case of an addition-elimination reaction, absolutely no problem kicking out methoxy group or ethoxy group, pKa of the conjugate acid 17. Great question. All right, at this point, I want to move on to the final point that I want to make in today's lecture, and to bring us to some ideas of synthesis and showing you how powerful organometallic reagents are in carbon-carbon bond forming reactions, but also the process by which organic chemists think about using these reagents and using reagents in general to build up molecules. And so I'm going to give you a little bit of a contrived example here, but it's very much like the type of thinking that people use as they become more sophisticated. So the example I'm going to give us is to synthesize a particular compound. I've chosen it as an example to illustrate a point, but indeed something very much like it could, say, be a useful insect pheromone that you might want to make for a trap for, say, Japanese beetles. So we're going to try to develop a synthesis of 4-ethyl-4-octanol from compounds containing 4 carbon atoms or fewer. There's nothing magical about 4 carbon atoms, but many, if you look at commercially available compounds, in general, most of them are small, and you can buy a whole range of different compounds. And more big and more complex compounds often are not as available. So you can buy many compounds containing 4 carbon atoms, or 3 carbon atoms, or 2, or 1. Of course, you can buy plenty containing 5, but for purposes of this example, we're going to say 4 or fewer. And what we're going to do with this is illustrate the way chemists think the process of retrosynthetic analysis and we can call this the process of thinking backwards about how to synthesize something. And the reason retrosynthetic analysis is so powerful, the reason that the process of thinking backwards is so powerful, is it's so easy to get caught up in details when you try to look at things from a forward point of view that it's very hard to see how to get there from here, from compounds containing 4 carbons or fewer. Oh, well, we're using organometallic reagents. Do I use an organolithium? Do I use a Grignard? Do I use an ester? Do I use an acid chloride? Do I use butyl lithium as a base? Do I use methyl lithium? So retrosynthetic analysis is kind of like thinking your way through a chess game. We're going to start with big pictures and then work our way to the details. So let me show you how I would think about this particular example. And you'll encounter on this week's discussion problems several examples very similar to this that involve processes of thinking backward at various levels of sophistication. All right, so let me draw out my compound. So it is, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So here's my target molecule. Now, when I first think about this, I could look at this and say, oh, well, okay, he said 4 carbons or fewer. And we just learned about addition of organometallic reagents to esters. So I could envision taking some ester. It would have to be a methyl ester of propanoic acid because that's 4 carbons. I couldn't use any more. And I could envision forming this bond by adding in butyl lithium. And maybe again, for the point of view from 5,000 feet or 30,000 feet, I'm just going to think in abstractions of some metal, whether it's a Grignard or a lithium, doesn't matter. And again, I could think, well, here we add in some metal, and that kind of catches the strategy. But we've got a problem here, and the problem is how do we get selectivity? I just said you can't really add one equivalent of a Grignard reagent or an organolithium compound to an ester. It won't stop at the ketone. Was that your question?
Oh, yeah, no, that's fine.
All right. So let me take this same idea and see if we can think backward a little bit. So we know, see here I'm trying to do it all at once. And I kind of got myself going here. It's a lot better than saying we're going to think forward. But let me think a little bit backwards. We know that an alcohol can be formed by a ketone and an organometallic reagent. So we could imagine, so I'm going to use this arrow here. This arrow This big open arrow means a retrosynthetic arrow. It means a thinking backwards arrow. Organic chemists love arrows. Curved arrows, equilibrium arrows, resonance arrows. This is a retrosynthetic arrow. So I could envision going ahead and going backward to this ketone. And I could envision, let's see, did I do that right? Nope. I could envision this ketone, 2-hexanone, and a butyl metal reagent. And that would work. I could add butyl lithium or butyl magnesium bromide to 2-hexanone. And that would be OK to make that alcohol. But then I'd need a way to make this ketone. And oh, well, OK, we could make that ketone. We've only learned reactions that form carbon-carbon bonds to make alcohols at this point in this course. So I could imagine making that ketone by oxidation of the corresponding alcohol of 3-hexanol. And again, right now, I'm not going to worry which reagent to use, whether I use chromium trioxide, whether I use potassium chromate, whatever. But now I look and I say, oh, wait, and I can think backwards again now to the point of a propyl metal reagent and propanal. And at the strategic level, we've now broken this molecule apart. We've used the process of thinking backwards to figure out how we can put this molecule together. And now, having completed our retrosynthetic analysis, now we're ready to go forward and worry from the strategy to the tactics of, OK, what reagent do we choose? How do we do our details? And so the last thing I'll do in solving this hypothetical problem is to show you the synthesis that I've worked out. So I would start with propanal. I've completed the requirement with each of my 3 components of 4 carbons or fewer. I've start with propanol. Propanal, it's commercially available. It fits the requirement. I'll add in, just for the fun of it, I'll use propyl magnesium chloride. I could use propyl lithium. I could use propyl magnesium bromide, propyl magnesium iodide. I'll carry out my workup with aqueous HCl. I could use aqueous sulfuric acid. I could use aqueous ammonium chloride. I could probably be lazy and write H3O plus over the arrow. But I'm going to go to the stockroom and get some chemicals, and I'm going to ask them for some HCl. The product of that reaction after workup is 3-hexanol. I now am ready to oxidize my 3-hexanol. You learned lots of reactions last quarter for oxidation. They taught you potassium dichromate in sulfuric acid and water, sometimes called Jones reagent. There are many, many reagents based on chromium-6, sodium dichromate, chromium trioxide. There are lots of safer alternatives, including alternatives based on bleach. But we're going to use reactions that you know, so we're going to use potassium dichromate. Then, at that point, we have our 2-hexanone and question.
I was just wondering, could you also, instead of the K2 and CR2, use just CrO3?
Absolutely. We could use chromium trioxide as an oxidizing agent. Lots to choose about from. Nice in our retrosynthetic analysis, not having to worry about getting that right yet. And now having the leisure of going and choosing our reagents and choosing our tactics. Finally, to complete our synthesis, I'm going to take butyl lithium, and I'll do an aqueous workup. And again, I'll use HCl. I've written it below the arrow here, written it above the arrow there. Doesn't really matter. A chemist is going to read it the same way. And lo and behold, I have proposed a rational and selective synthesis of our target molecule for ethyl 4-octanol. And this art of recognizing something in a molecule and seeing where it comes from is going to grow and grow in the course. Right now, we've seen an alcohol, and we said, oh, I know how to make an alcohol. I can make an alcohol by adding in 2 carbon nucleophiles. I can make alcohols by adding in carbon nucleophiles. Later on, we're going to see all sorts of other families of carbonyl compounds. All right, I will see you on Thursday. We'll start off with a 10-minute quiz.